Okay. Hello, hello, hello. Anyone there yet? Just gonna wait for some people in the chat to come into the chat. Today is a live show. It's been a long time since I had a live show. Testing, testing, testing. Anyone there? Anyone there? Just let me know. You can put a comment in the chat below. Just want to know if I'm not speaking just to myself. Okay, got one and then they left. This is a live show. If anyone's going to come in, it will be greatly appreciated. We are going to be doing, I haven't had a live show in a while, actually. I took a break from live shows that I've done mainly lately, just regular recordings of my brand. Yeah, that's about it. Live shows, I notice, can be a bit taxing sometimes, especially in mathematics. Have to set up all sorts of stuff, I noticed. But I'm going to be doing more of them. I'm going to do them every 2.5 weeks. I think is a good, yeah, I'm going to do 2.5 weeks. Anyone coming in? So let you know, we are looking at, today is an interesting live show. We're going to be looking at an exclusive problem from my book. Okay. Now, it's not the first one, but it's one of the many from my book that is unique. So as long as you have a working knowledge of integral calculus, you should be fine today. And when I mean working knowledge, I mean like a strong foundation, not weak. Strong foundation. And if you did really well in integral calculus, you're going to be able to follow what I'm doing. But don't worry, I will take it light today. Today is going to be a light day. We're mainly just going to do some frameworks and sketchings of the problem. That's it. Okay. So for those of you who are interested in, you know, whether it's recreational, whether it's you're looking, you have a hard exam and you don't know how to tackle some of those integral problems that make you freeze, today may be a good, maybe a very good day to look at that. And a problem that would probably pop up. That being said, I don't know about this problem per se. Your professor would have to be a really devilish person to put this up on a first-year exam at the end of the exam. That being said, you can still ask it. It's to come to a solution. It's a special type of integral. It's called an elliptic integral. But we are going to take it, I'm going to take it light today again. I'm not going to make it overly taxing, okay? Because I feel like a lot of people either, you know, they can't follow along or they lose interest. So I'm not going to make it overly taxing. but we're going to talk about the main concepts of this cool integral, okay? From my book. I should actually have my physical copy with me. I should actually get my physical copy from the supplier that I deal with. Yeah, I have to get it from them. Oh, hello. We have someone in. Testing. Put something in the chat if you're there. This helps me feel like I'm not talking to myself for the moment. I'm just waiting for some people to come in. Okay, we got 2 people. Okay, 2 is good. Okay, so we are going to, today is going to be a light day, okay, as I mentioned. And I haven't done a live show in a while, but it's going to be a light day in terms of the mathematics involved, okay? I don't mean like light in terms of the mechanics of the math that's involved. I'm mainly going to be taking it light today. We're going to mainly talk about the interesting concepts of the elliptic integral, its applications, and for people who have general interest in learning, calculus. Okay. So today is going to be a little bit of a transition. Normally, I'm helping students with specifically hard midterm and exam questions. Okay. Today is going to be mainly about, for those of you who have general interest in learning advanced mathematics, and you've done some yourself, and you want to be able to take it to the next level, this is the place to be. Okay, so that's what we're going to be doing. All right. So I might as well get something on the board. Okay. Just give me a moment. We're going to go to, let's use the whiteboard. Use the whiteboard. Let me know if you guys can see the whiteboard. Okay. It's all the way up. So today, let's see here. Just give me a sec. Yeah. So let me just see my desktop. Let me know if you can see what I'm writing. So today, as I mentioned, is going to be on the elliptic integral. Elliptic integral of the second kind. Okay, so the elliptic. Sorry about that. Elliptic integral. Integral of the second kind. Of the second kind. Okay. Now, this problem comes from my book, okay, that I've emphasized here, called Advanced Integration Techniques, okay, where we're going to be looking at, my whole book is like this. It's mainly, this book here, I only advise it for people who are really strong at first year calculus and linear algebra, okay, because it gives you, it's a challenge, right? This was not meant to be easy whatsoever, okay? It's a hard book. But if you've done really well in calculus and or linear algebra, then you're just building your knowledge, and not just building your knowledge. There's also questions that will open your horizons when it comes to thinking abstractly. Okay, let me know if anyone's in. Okay, yeah, I see there. Let me know if you're able to see what I'm writing on the board for the viewer. All right, so if you can see me doodling at the moment, let me know. Okay. So we're going to be looking at the elliptic integral of the second kind. So as I mentioned, this book here, right, is a collection of every type of integral in undergraduate mathematics that you would come across, right? Whether it's integration by parts, complex integration, doesn't matter. It has it. Okay, and it's a very definition and theorem. It's somewhat of a definition theorem proof book, but it's not too heavily definition theorem proof. Okay, because there's also a lot of applications where you have to compute things and stuff like that. Okay, And as I mentioned, this book is for those of you who want to be challenged, okay? Or those of you who just want to be learning more, building a mathematical toolkit, but not just a mathematical toolkit, a toolkit that is based on problem solving, okay? If that makes sense, all right? So let's look at the elliptic integral of the second kind, okay? So let me put it here, right? So the problem is, right, we want to be able to compute this, okay? So let's put this over here. Problem is you want to be able to compute this guy right here. Okay, so E of, use like this, E of k comma phi. Okay, so k is a parameter or a variable, right? So k comma phi, okay? And this is equal to the integral from 0 to phi, all right, of the square root of 1 minus k squared. So with that, let me see here, k squared. I have to get a better pen, otherwise this doesn't help us. K squared sine squared theta d theta. Okay, that's what an elliptic interval of the second kind looks like. There's three types of elliptic intervals: the first, second, and third. Okay. Now you're probably wondering, where on earth does this come from? Oh, shit. Let me see here. Can't see what I'm writing. Okay, let me just go back. Sorry about that. Sometimes things happen. Just give me a sec. That's our screen. Go to the window. What is here? The entire screen. Okay, show the entire screen. Okay, and then we're gonna do this. What about now? Can you see what I'm doing? Just put something in the chat. Just let me know if you can see anything. Okay, perfect. Excellent. So that's the way to do it. Okay, so as I was saying, right, before we jump into this problem, this book here, Advanced Integration Techniques, is a very comprehensive book on undergraduate calculus-based courses, specifically integration. Okay, so again, I'm just putting out there that this book was meant for students who already have a strong foundation in integral calculus and linear algebra. That's all you need. Okay, I'm assuming, obviously, if you have those, I'm assuming you took university or are in university for something like engineering or mathematics. But if you have strong foundations in both of those, you'll find this book really helpful. Okay, helpful for recreational use, helpful for hard midterm or exam integrals that you may come across in your courses, especially if you're in engineering. I know in engineering, you guys have to eat integrals, if that makes sense. Like I say, but yeah, integrals is like your bread and butter in engineering. Okay, and physics too, right? It's pretty much a mathematical methods book, if any of you know what I'm talking about, right, or refer to. But it's as harder, I'd say harder in terms of the difficulty. So it requires you to think in a very creative foundation, if that makes sense. Okay. Right. So we're going to be looking, that's what today's lecture is going to be on, right? It's going to be on looking at a specific problem from this book. Let me know if you have any questions. Okay, I'll just go back. All right. So I'll go back and forth. If someone puts something in the chat, I need to see it. So I have to minimize out of the whiteboard. And yes. Okay. So, and it took me, what was it? A long time to write this book. It was nasty. Oh, God. What a headache. I should have brought actually the physical. I have the physical. Next time I'm going to do that. I'm going to get my, what is it called? Print on demand company, send me a physical copy that I'm with. Send me a physical copy of the book so you can see it. And I can go through page for page. It's always good to actually hold the book in your hands. I feel like there's more of a connection with people, and they say, "Oh, damn, that looks cool," and they get to see what's actually in the book. You know what I mean? So I think, we can always go through that. All right. But anyways, let's get right down to the bulk of today's live show. All right. So we're going to be looking at the elliptic integral of the second kind. If you don't know what that is completely fine. But if you understand integral calculus to a pretty good degree, you're going to follow what I'm saying here today. Okay. Any questions? So I can start. Okay. I don't think there's any questions. All right. So we're going to get right to it. So we're going to look at the elliptic integral of the second kind. So where does this integral come from? Right? What's its use case? So this integral actually came. I'm just going to erase this right now. For now, I'm just going to put something very interesting. Okay. Right. The elliptic integral. All right. So I'm just going to put over here. So where did it come from? So where did the elliptic integral come from? Integral come from. All right. Now it came from, actually, and I sort of put this in my book, not that much of a backstory, but a very, very, very small backstory. And that is, it came from the fact of experts looking at the arc length of an ellipse. Okay, that's where the elliptic integral came from. And actually, even if you don't know that per se, you can make some sort of, some sort of comparisons to the way that formula look like. Watch carefully as I do this. To calculate the arc length of anything, right? Let's say arc length S, okay? Especially if it's constantly changing, all right? So I might do this actually, like this, put some graph here. Let's say you have some sort of ellipse, okay? Right, something like this, X, Y, okay? And that arc length here, right? Let's say you want to calculate the arc length, okay? Remember what an arc length is. You may have some sort of sector here. Let's say I call this, colored in blue, okay? Sector from here to here, okay? And I'm going to color code it red. Let's say I'm calculating some arc length here, okay? And I'll use yellow over here. That yellow part here that I'm pointing to, that is my arc length S, if I can zoom in, okay? Does that make sense? All right. So my arc length S. So my arc length S. This elliptic integral, okay, came from calculating the arc length of a very interesting geometric structure, the ellipse, okay? Now, as I mentioned, the arc length can be calculated by using S. S is equal to the integral from A to B of the square root of 1 plus, on parentheses, dy dx all squared dx. Okay? That's how we calculate arc length of anything. Question? Someone has a question. Those retracted. Let me know if you have questions in the chat. We are looking at an interesting problem from my book, The Elliptic Integral of the Second Kind. Don't worry if you have never heard of it and you don't know what the hell it is. As long as you have a foundation, strong foundation in integral calculus and linear algebra, you're fine. Well, for this case, you don't need to have the linear algebra, but if you're a calculus-only person, you'll be fine. There's no question. Okay, I'll continue. All right, so, and don't be shy. Pause me, right? Pause, ask questions, critique something, question me. Like, yes, I wrote this, but at the same time, I'm prone to mistakes too. Okay. And also, maybe there's something I don't know. None of us knows everything, right? We're human after all. We need to be learning from each other through dialogue, right? Actually, that's the best way to learn anything, right? More than books. That's why I'm doing this live, right? Is because when you do something live, you actually having a real conversation with somebody or multiple somebodies sometimes. Okay, so if you look at calculating the arc length, right, of the ellipse, right, that's how we're going to get that integral that I mentioned. Okay. Now today we're not going to prove that very result, the elliptic integral, but I'm going to talk about how you compute it, like the calculation behind it. Okay, but it came from, I'm just giving you a historical reference. It actually came from mathematicians looking at the arc length of ellipses, okay? So this actually came from, right? This investigation of the elliptic integral. This investigation of the elliptic integral. Elliptic integral came from mathematicians. In wanting to investigate the arc length, investigate the arc length. Arc length of an ellipse. And back to a little bit of a thing for some of you who don't know, equation of an ellipse, right? So the equation of ellipse, especially one that is horizontally elongated like the one I have here, right? With a major axis as follows. Let's see over here. This is the major axis. Okay, and the minor axis is on the y-axis. Let's see here, the y-axis. So it's the minor. This is the major. Any questions? Okay, no questions. All right. So right now we've gotten, just talking a little bit, still the backstory a little bit, and some equations to make sense out of some things. So the equation of an ellipse, at least when it's on its horizontal axis, okay, like the one that I have over here that I'm zooming in on, okay, can be represented by the following equation. And that following equation is x squared over a squared plus y squared over b squared is equal to 1. Okay, that's the general equation of an ellipse. Ellipse along its major axis, I should be saying. This is an ellipse along a major axis. But anyways, I digress, okay? So the elliptic integral of the second kind is what we're going to be looking at. Okay, so let us go to the next page. All right, so we're going to go to a new page. So the elliptic integral of the second kind is this guy here. Okay, so we're going to look at it. So elliptic integral. I'm lazy today, so I'm just going to say second. There's 3 types. Right. Now, there's multiple ways of how to get. It's very interesting, this type of integral, actually, and it's it's very interesting. You can either calculate this integral that I'm going to write down right now, right? So it is using the form the elliptic integral of e as a function of k and phi is equal to the integral from 0 to phi, the square root of 1 minus, what is it again, k squared sine square theta, and then d theta. Okay. All right. Just one sec. I like to make I think I work better. K squared, my writing. K squared sine squared theta d theta. Okay, so we're looking at this integral here. All right. And we want to know how to calculate it. We want to be able to, well, I mean calculate, I mean like get an even simpler compact expression of this guy. Okay. Now, let's go through that. All right. So let's look at this guy here, unless any of you have ideas of how to calculate this. So notice how I'm labeling in green something. Why am I focusing on this the expression, the integrand here? Actually, I'm going to give a hint. I'm going to calculate what this is. And when I mean calculate, I mean like do some sort of expansion. But in order to expand this, we first need to expand this guy. Anyone has any ideas? Anyone have any ideas of how we can calculate? And when I mean calculate, I mean expand this integral. Anyone have ideas? Please let me know. Again, for anyone coming in, we're just looking at a interesting integral, very interesting integral calculus problem from my book, Advanced Integration Techniques. Right, and we want to be able to expand this integral. Anyone have any ideas? Let me know. Don't be shy. You can put something in the comments. Okay, so I will do it myself then if no one has ideas. We're going to make this expression now be equivalent to 1 minus k squared sine squared theta all to the 1/2 power. I did that because it's the same thing as saying the square root power. I can raise this all to the 1/2 power. Damn it, I need to get a better pen. My writing isn't as good. Let me try to make this even nicer. Just one sec. So 1 minus k squared sine squared theta to the 1/2. Right? I can write it like this. And don't worry for those of you who don't know or shy, or maybe you do know, maybe you know a lot, but you're just too shy to share the information, or you doubt yourselves for A or B reason or whatever. Don't worry, I was like that at one point. Mathematics was a nightmare for me in grade 8. Oh yeah, grade 8 was an absolute nightmare. Doesn't help that past years I didn't have the greatest teachers. But it wasn't until I actually came across two teachers that actually changed my life. Okay. And they taught me a way to do mathematics. I mean, like, there's no silver bullet cure for doing this stuff. Okay. There isn't. Um, there is no silver bullet for learning mathematics. There's no fast way to do it. There isn't. But these two teachers in grade 9, it was grade 9 and it was grade 10. And they told me that, first off, don't get anxious, because when you get anxious, your mind is not going to be able to clearly think through any problem, not just math, but any problem whatsoever. Okay. So you want to be able to sort of like be able to have confidence in yourself, rational confidence. I don't mean stupidity. And be able to sort of like say, okay, I have clarity. That's what I'm talking about. Okay. And then once you have that clarity, right, you can apply a system. You can't do math without applying a system. Okay, maybe if it's extremely basic, but even then, there's always some form of problem solving that you need to be able to think logically, right? So you need a system, okay? And the system that I learned in school was called something called the systems technique, okay? So I'm just write this down. I learned something called the systems technique. Let me just, before I calculate this, because it's really important. Systems, so the systems technique. Systems technique. And this changed my life. I went from being a junior high school, almost like I wouldn't say dropout, but really bad student, to becoming an A student in university. Okay, so systems technique. And not just A student, well, A, yes. Made my GPA go up to, university I did phenomenal. I got a 3.85 to 3.9 GPA. Right, so clearly something helped. I just always try and use the system best. Again, it's not a silver bullet thing that solves every problem, but it gives you clarity on how, like a framework of how to solve problems. Okay, so number one, you want to be able to visualize. Okay, let's do that. So number one, visualize the problem. In other words, this systems technique is an excellent way, okay, to think in pictures. Most people think, oh, math is formulas, equations. Baloney. Absolute baloney. Well, you can still solve at the very basic problems. Yeah, you can solve them without using pictures or language or whatever. But the real math that you do, like, and I mean real math, math is supposed to be hard. It's not hard. You're not choosing hard enough problems, and your teacher is setting you up to fail. Right? Real math is about pictures, visualization, and language. Pictorially be able to visualize things and then be able to communicate it in a very precise way. Okay. All right. So for any mathematicians in the audience, you'll know what I'm talking about, right? You have to be able to speak in a very precise way when doing mathematics. All right. You almost have to speak in a way that's almost to the point of perfection. That's how crazy it is. Okay. You have to be very precise, right? And not just your speaking, but your thinking has to be very precise as well. They're synchronized. Okay. So the first step is the visualization step. I sort of gave you in this problem, sort of where this comes from. Okay. At least a visual anyways, right? Of the elliptic integral, right? So looking at an ellipse that I have drawn on the first page here. Okay. And I cut it. I made pie piece, as you can say, like these two blue triangular parts there, right over here, this guy over here. Okay, and I shaded it in red to show the sector that we're dealing with. Now, the outer part here, right, that I've colored in with the yellow, is some sort of arc. It's an arc length. Okay, so that's pretty much, that's how we get to this integral here, actually, is that mathematicians were looking to calculate the arc length of an ellipse. Okay, and they were able to get to this. Any questions? Any questions whatsoever? All right. So we're looking at, again, so I did the visualization step. That's step one. You want to be able to visualize this. Okay. Now, we can do more in terms of the visualization here. If anyone can think of anything. You'll notice that this elliptic integral is a trigonometric integral of some sort. So is it a regular trigonometric integral? Is it an inverse trigonometric integral? I will let you guys think about that. I'm not going to do all of the thinking. Right? I want you guys to communicate with me. Okay. So I'll let you guys figure that out for step one. So the visualization. Step two, right? We want to be able to model what we are dealing with. Now, most of you might think, okay, isn't that the same as visualize? No. Model is giving you a semantic, a linguistic framework of the knowns, unknowns, things that I need. And not always knowns and unknowns, but important things to extrapolate. Okay? Because quite often in math, you can be given a problem, you think all those variables need to be used, or all those numbers, and quite often you don't need them, or you have to invent a variable or something like that. Okay? And that's where people get like, oh God, this is intuitively very difficult. But it's a reality that we have to be able to, be able to come to fruition with. Okay. And number three, we want to be able, this is very important, we want to be able to verify what we are doing, what we are saying. Okay. Now, as I said, this systems technique it's a system. It's not a direct 100% formula that's going to tell you, okay, visualize, but you have to know what to visualize. You have to know what to model. You have to know what to verify. You have to know the questions to ask. Okay. That comes from you though, right? This is just a strong framework. Right? Any questions? All right. So verify, you want to be able to verify your work. And what I mean verify, it can either be like, let's say maybe if it's more simple, left hand, right hand, just like if you had a linear equation, right? Left hand, right hand. If left hand equals right hand, you're on the right mark. If not, you have a problem. Or you can figure out if something, especially if it's an application problem, if physically something doesn't make sense. Okay. Like do the numbers, they may make mathematical sense to you, but they may not make physical sense. So that's why verify is important. Okay. And then 4, you want to be able to execute your strategy. I think that's obvious. You don't have to get into 4. I'm going to connect them like a chain. Okay. So the systems technique. All right. So let's get to this guy over here. We want to be able to expand this. Now, for those of you who don't remember, you should remember what the binomial theorem is and why I'm going to use it. Okay. So that will be, we're looking at almost the modeling step right now. I'm going to put a asterisk. Okay. We'll look at the modeling step because I know when you model, I have to figure out what I need to do. What is my sort of a plan of attack when it comes to this problem? So I noticed that since we were asked to expand this integral, okay, then that means I first need to focus on expanding this guy. Okay, squared sine squared theta, this guy here, okay? And the best way to do that is to rewrite it, 1 minus k squared sine squared theta all to the 1/2, unless there's any dispute about that. Have disputes. Anyone have disputes? Okay, so right now we've got this guy right here, okay? Now, if we want to expand this integral, as I said, I expanded the integrand, right? This piece here that I highlighted in green is my integrand, okay? Now, we have this piece here. I rewrote it to the power of 1/2 because it's the same as the square root, okay? What I'm going to do now is apply the binomial expansion, okay? So I'm going to write here, we're going to use binomial expansion. So we're going to use the binomial expansion. Something from grade 12, grade 11 or 12, I can't remember. Used to know what it is, right? So it's usually in the form, anytime when you have an algebraic expression written like this, 1 plus x all to the nth power, okay? And it is equal to 1 plus n times x plus n times n minus 1, okay? Divided by 2 factorial times x squared, just 1 second, times x squared, plus n by n minus 1 times n minus 2 all over 3 factorial. You can see the pattern pretty much, times x cubed, plus dot, 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 and so forth. Any questions? Anyone have questions? Okay, so we have a binomial expansion here. Okay, now, this would be a good question if some of you have, if you can't make this distinction. And it's very important to make this distinction in mathematics, right? Is knowing what formula or theorem to use when. A lot of you will say, but I thought the binomial expansion was this. I thought it was just x plus y all to the nth power is equal to the sum from k equals 0 to n of n choose k, x to the n minus k times y to the k. Anyone figure out why I didn't use 2, but I used number 1? So this is equation 1, equation 2. So why am I using 1 instead of 2? 2 is the regular binomial expansion. Why am I using 1? Anyone know? Anybody know? Okay. The reason for this is because of the 1 in my expression. So this guy here can be written in terms of 1 plus x to the n, where x is equal to k squared minus k squared sine squared theta, right? That's all I'm doing. Okay. So I'm setting x equal to negative k squared sine squared theta. Okay. And then by that logic, it's very simple. Then I'm getting the 1 minus k squared sine squared theta all to the 1/2. And this is equal to 1 plus 1/2 because n is a half. 1/2 times x, that negative k squared sine squared theta, times negative k squared sine squared theta. Okay. All right, as you can see here, plus n, which is 1/2, times 1/2 minus 1, okay, all over the 2 factorial, okay, x squared, negative k squared sine squared theta all squared, right? And then plus n by n minus 1 times n minus 2 all over 3 factorial, which will give me 1/2 times 1/2 minus 1 times 1/2 minus 2 all over 3 factorial. factorial times negative k squared sine squared theta all cubed, as you can see, plus dot, dot, dot. Okay, we have to clean this guy up here. Any questions? Okay, so we've got this. You'll notice from here we get an obvious expression. It's going to be 1 minus 1 over 2 k squared sine squared theta, right? This 1/2 minus 1 is negative a half times a half. It's negative 1/4, negative 1/4 2 factorial 2. So that's like negative 1/8. Yeah, negative 1/8. Negative 1/8 of k to the 4 sine to the 4 theta, right? So just distributing this in, okay? Then we have over here 1/2 minus 1 is negative half, so we get 1/2 times negative half times, so we get negative 3, negative 3, yeah, negative 3, negative 3 over 2, okay, all over 3 factorial. That's going to give me 6 at the bottom. 2 is 4, 4 3. Yeah, and then after k squared sine squared theta all cubed gives me negative k to the 6 sine 6 theta. And we just keep continuing. Any questions? Okay. Now, if you, this is going to be plus dot, 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 right? Some sort of infinite series that keeps going. Okay. Now, what this becomes, right, on the next page, right, is that you're going to get 1 minus k squared sine squared theta, right? Theta all to the 1/2. I need a pen instead of using my finger here. Okay. Let's over here. What this becomes is, if we clean up from the previous page, okay, it becomes 1 minus 1/2 k squared sine squared theta. So 1 minus 1/2 k squared sine squared theta minus 1/8 k to the 4 sine to the 4th. Theta. Let's see what that is. 2 8. 48. 48. 3 out of 48 gives me 1/16. Positive 1/16 k to the 6 sine 6 theta. Positive 1. So positive 1/16 k to the 6. K to the 6. It's doing the algebra fast in my head. Okay, 6 sine to the 6 theta plus dot, dot, dot. Okay, any questions on how I got that? Okay, so this is what we've simplified it to. Now, we have to look for a general pattern, right? Because right now we have all this. Most of you will think, okay, I have this guy right here. Okay. And that's our replacement for, because we have a binomial expansion for this guy here. Not quite yet, right? I mean, we could do that, but it's going to be painful substituting that in and then integrating each term by term. And do you really want to integrate sine to the 4, sine to the 6, and so forth? It's a bit annoying. So we can look for a general pattern in this. Okay, so let me just write some stuff out. 1 minus 1 over 2 k squared sine squared theta Okay. All right. Now, for this portion here, that 1/8 was calculated with something, and this 1/16 was calculated. Originally, this was like 3/48, by the way. I just simplified. That was 3/48. Okay, the portion I'm circling here. Right? This was like 1 over something. It's like 1 over, I'm forgetting 1 over something, right? But you'll notice in the numerator, if you look carefully, it goes from 1 to 3. And I suspect that the next guy will go to 5 in the numerator and then to 7. Okay. You'll notice that there's a general pattern here, correct? There's a general pattern. And that pattern is, I'm just going to highlight this, is that it's a multiplication of n number of odd numbers. 1 times 3 times 5 times ... parentheses 2n minus 1. 2n minus 1, because this makes sense. So odd numbers starting at n equals 1 would give you the whole range of odd numbers, right? Divided by the denominator. Again, the denominator is 2. This was initially not 8. I'm breaking it up. 4 by 2 made 8. Use 2 there, so it's going to be 4s. So 2, 4. And then this guy, we will assume that was the breaking of 6. So it goes 2 times 4. So far you see even numbers, times 6 times ... 2 to the 2n. Okay? Times, because we still have these expressions, times k to the 2n, where n starts at 1, because if n starts at 1, that's how we get that k squared, and then sine 2n theta. Okay? This is a ... by the way. This is not minus. This is like minus ... because we're going up all the way up to n numbers questions. Okay, so this is what we got right now. Now we have all this, okay? But what can we do with it? What are we going to do? Like, we can substitute that in. Well, we are going to substitute this information. So sub. We're going to substitute back into our integral. So our integral that we dealt with was that we had an integral from 0 to pi over 2, right, of the square root 1 minus k squared sine squared phi d phi. Okay, so d phi, our elliptic integral of the second kind, this can be replaced now by saying integral from 0 to pi over 2. This square root part here can be substituted with this expression, 1 minus 1 over 2 k squared sine squared phi. Okay, we're replacing phi with theta, because initially the integral was going from 0 to phi with respect to theta, but we want to calculate an actual elliptic integral always is in terms of phi, and the boundaries go from 0 to pi over 2. So 1 minus 1/2 k squared sine squared phi. K squared is phi, and then minus ... 1 times 3 times 5 times ... 2n minus 1 all over 2 times 4 times 6 times ... 2n, as you can see here. And then we have that k to the 2n sine to the 2n of phi. Integrate the whole thing with respect to phi. Any questions? Oh, that's a lot to swallow. Any questions? Okay, so this is what we got right now. So yeah, that looks nasty. But numbers don't lie. That's what we've been able to come down with. Please let me know if you have questions in chat. Anything you want to dispute, anything you want to ask, anything you don't know, anything that, like, where is this coming from? I'm going to be right back. I need to get some water. All this talking dries out the throat. Okay, so if you look at our integral here, all right, so this is what we've been able to come down with. Let's see if anyone new came in. No, nothing yet. All right, so we got this guy right here, okay? Now, we can always expand, right? We can expand all this, right, if you want to. Still nasty. Why would we do that? That would just be that would be torture. However, we should notice something since we're integrating with respect to phi. Notice that the integral, I want to use yellow guy. Notice if I take the integral from 0 to pi over 2 of sine to the 2nth power of phi d phi, this is equal to something that we already know. It's actually equal to 1 times 3. Okay? It produces the same pattern. 1 times 3 times 5 times dot, an even spacing of odd numbers to n minus 1 over even numbers, 2 by 4 by 6 by, and then dot by 6 by dot 2n. This will actually do that. Okay, if you're to integrate this guy here, it will give you something of that nature. Okay, any questions? And this is going to be a multiple of pi over 2, right? This is going to be multiple of pi over 2 because if you integrate this, it's always going to give you some multiple of pi over 2. Okay, so we have some multiple by pi over 2 with all these ends. Even the odds over the evens multiplied by pi over 2 gives you this integral on the left-hand side, which we would have to calculate at some point, this guy here. Okay. Any questions, please let me know. Again, for anyone new coming in, I am taking up the elliptic integral problem from my book. You can also find me on LinkedIn. For the last 2 weeks, I've been talking about my book and the elliptic integral problem. And I want to share how you'd go about it, how you'd expand it, the backstory of the elliptic integral problem. It's really interesting stuff. Okay. All right, so we have the integral from 0 to pi over 2 sine to 2n phi d phi, right? And we've gotten this craziness. That's what the answer is to this portion. Now, why did I do that? How come I didn't just multiply all of this together? Well, I'm not going to. I'm going to do it case by case, like multiply, FOIL in each integral and calculate the integral for each one. That's annoying. But I will replace k to the 2n sine to the 2n phi. Sine to 2n phi, I already know what it is. I just got it. It's a multiple of odds over evens multiplied by pi over 2. Okay? Almost like what we got over here, right? Almost. So we're going to replace sine to the 2n phi with this. Okay? So let's do that. So nothing complicated. Integral from 0 to pi over 2 of the square root 1 minus, well, I don't need to do that. It's extra work. We already know what it is. We were calculating this guy 1 minus 1 over 2 k squared sine squared phi, okay, minus dot plus 1 times 3 by 5 times dot times 2n minus 1, where n starts at 1, over 2 times 4 times 6 times dot 2n. Okay. And we're replacing that sine to the 2n. Don't forget, I used to put a k. The 2n is still there. No substitutes. Yeah, that I left it alone. Replacing sine to the 2n with this guy here. Okay, so this now becomes multiplied by 1 times 3 times 5 times dot of 2n minus 1 all over 2 times 4 times 6 times dot 2n. Let me see if that's good. Yep. And then multiplied by pi over 2. Any questions? Can you do the cube root of n? I didn't see that question. This came up right now. Is that a new person? Can you do the cube root of n plus the square root of n squared plus 8 all divided by cube root of n minus square root of n squared plus 8? That's a very good question. Yeah, so Lucas, if you're still here, I don't know if you're still here though. It doesn't show anyone that's here. Lucas, put something in the chat. If you're still here. Lucas, put something in the chat if you're still here. It's sort of have me in the loop. I didn't see your question earlier. Just now, just getting caught up in the algebra. If you can put something in the chat, just let me know you're here. But yeah, to answer your question, if you're here, I don't know. I wasn't talking to myself. Can you do the cube root of n plus the square root of n plus 8, all divided by the cube root of n minus the square root of n plus 8? You want me to answer if that's allowed, you're saying? Is that what I'm getting here? You want me to answer if that what you're saying is allowed? Lucas. Well, what you gave me was a question that, in terms of, well, no, because first off, the question is sort of a bit of a semantically null sentence, right? Let me see. Cube root of n. No, that doesn't give you anything, right? So that no, you can't. No. there won't be, and there won't be any significance in that expression anyways, but no, you can't do that. Mhm. All right, so I'm gonna go back. Okay, so you got all of this. Okay. So we've come down to an expression that looks pretty uh pretty nasty. Okay. It's a pretty nasty uh integral that we have here. Let's not get ourselves to think that, oh, okay, this is a nice integral. Well, it is. This looks a little scary, but it's not as scary as people think it is. All right. So let's go back to whiteboard. All right. So this guy over here. So we have all this mess. Okay. All this mess. We're going to be able to simplify it even more. So for anyone who's watching this live show, or sometimes no one has to watch it, but then there's a bunch of people who watch it after once it's already aired, I am giving you a question. Try to solve it. Try to simplify this even more. This will enhance your simplification techniques. Okay, try and see if you can dig deeper into this problem. Okay, all right. So for those of you today, it's been a long time since I've done one of these live shows. Okay, see, it's been a little too long. I've taken a break from doing live shows and just doing regular recordings. The live shows are usually about I don't do them often, but usually about some details in my book, Advanced Integration Techniques. Okay, so if you are either a undergraduate student or an independent learner who wants to uh, learn calculus, right? Learn integral calculus rigorously. This is the book for you. It's a comprehensive book, all levels of integral calculus. Okay, so and it's going to help those of you who want to learn more build your toolkit. Okay, like theorem definition, but also very interesting problems also for students you want to challenge. If you want a real challenge, you have your and you're really good at integral calculus and linear algebra, might as well want to pick up this book. This book will give you a um, really strong foundation in these areas. Okay, all right. So this book, uh, and it's not that bad. You can get it either on uh, my website link. Link will be is in the description after this live show, or Amazon or wherever. Those links will be at the end of this live show. Okay. But again, this book is for undergraduate students. Okay. Undergraduate students who either want to learn more on integration, specifically for hard exams or midterms, because you always have those, 1, 2, 3, 4, or even 5, 6 really hard questions on your test. And it's going to challenge you. Right? Math is a challenge. Life's a challenge. Right? As a coach, I know that. I am a coach. I'm a coach and an author. But yeah, life is a challenge. It's a reality. And the harder challenges that we want to embrace, the better off we will be down the road. Okay? Don't run away from challenge. Invite it into your lives. Okay, you literally want to invite it in. Again, thanks again for joining this live show. For anyone who was watching, has watched, or will watch later on, there's going to be plenty more. Well, They don't come very fast. It's like every second to third week I do one of my live shows. But when it comes to regular content for undergraduate students needing help with calculus and physics problems, hard exam and midterm problems, I'm always on twice every week. Okay, so look for more of that regular content. It's coming up next week. But besides that, please like and subscribe. Again, I thank all my subscribers for keeping the channel relatively strong. Could be stronger, but like and subscribe, and I appreciate everyone who has subscribed. Okay, check out the book today. It will be in my link tree below. All right. Have a great weekend, guys. All right. Bye-bye.